Welcome to Part 5 in the module on Patterns and Frameworks for Concurrency and Synchronization. In previous parts of this module, we started by describing the active object pattern and exploring the ACE task framework that can be used to implement active objects and other concurrency patterns. We then talked about how to apply the ACE task and ACE acceptor connector frameworks in order to be able to implement a thread per connection version of our web server. Next, we talked about the half-sync, half-async pattern, which combines the reactor with active object. And now we're going to implement half-sync, half-async using a number of frameworks in ACE. This particular example will provide yet another path through our pattern language for web servers. This particular path will be, as you'll see, more scalable, realistically scalable than some of the implementations and patterns and frameworks we've looked at before. This particular example will start by exploring the use of the ACE service handler in order to be able to provide the reactive portion of this half-sync, half-async pattern. If you recall, we have a reactor portion on the bottom and an active object portion on top. And we'll start by talking about the reactive portion. There are a lot of pieces to discuss in this particular example, and so it's important to have an understanding of the pattern in order to figure out how the pieces interact with each other and how they're structured. Let's first start by talking about defining the TP HTTP handler class. TP stands for thread pool. In this particular case, the TP HTTP handler class is going to inherit from ACE service handler, and that means we can dispatch it from the reactive part of our system. It then goes ahead and defines a reference to an active object called TP HTTP task that we'll be talking about shortly. And that reference is tucked away as a data member in the implementation of this class. We then override the open hook method, which will be used by the ACE acceptor framework in order to activate this particular object after a connection is established. Now, when this occurs, what we're going to do is we're going to do two things. First, we're going to register ourselves with a reactor to be dispatched when an incoming event shows up containing a GET message. And we're also going to go ahead and schedule a timer. And this timer is used to guard against situations where clients provide some kind of intentional or accidental denial of service attack, where they connect to our server but never send any GET requests, and therefore we'd end up wasting resources. Let's first take a look at how we might implement the handle timeout mechanism. If the timeout period elapses, which could be whatever you want it to be, 30 seconds, a minute, 10 minutes, 2 seconds, whatever you think is appropriate for your workload environment, the reactor will go ahead and call back the handle timeout hook method after that timeout elapses. And what we do in this case is we use this as an opportunity to shut down that particular connection and reclaim any resources that have been allocated dynamically to prevent those types of denial of service attacks. More likely, however, we're actually going to get a GET request. And when that occurs, the reactor will call back to the handle input method on our TP HTTP handler class. And this handle input method will do several things. The first thing it'll do is it'll try to receive the complete message from the socket endpoint. And this may actually take a number of tries, because we can't afford to block here because we're in the half-async layer, or the reactive layer of our solution. Assuming we get the complete message, then what we do is we cancel the timer, remove the handler, and we take the message that we got and we pass it up to the half-sync layer using the put method that is invoked on the thread pool HTTP task object that we've got a reference to. This put method represents the boundary between the half-async part, or the reactive part, which is single-threaded and runs with callbacks from the reactor, and the active object part, which, as we'll see in a moment, is actually multi-threaded and runs as an active object. So let's now take a look at how we can implement this half-sync layer using the ACE task class. So once again, we have our half-async part, which we're using the reactor. And now we're going to go ahead and focus on illustrating how to implement the half-sync portion of our half-sync, half-async solution using ACE task, which will spawn a pool of threads. So let's first define the TP HTTP task class, where once again TP is thread pool. As you can see, this particular class inherits from ACE task, and it provides a special set of traits. And these traits are used to indicate that it wants to use the multi-threaded synchronization capabilities, which essentially means we're going to have a synchronized request queue. And we'll talk a bit more about that as we go further along. We then go ahead in the constructor of this object and we activate it to become an active object. And as you can see here, we're going to spawn 8 threads, and these threads will run in a pool in the background, and we'll look more at that in just a moment. When the put method is invoked on this particular active object as part of the handle input phase in the half-async portion of our design, that put method is going to turn around, take the message that is passed in, and then put it or enqueue it onto the thread-safe message queue. And that will then be used to feed in to the method that we'll look at on the next slide. We'll explain how this synchronized request queue works in the next part of this module when we talk about the monitor object pattern. Here is the key driver for this half-sync layer. This is the service hook method. This method will be called back once in every thread that's part of the thread pool. And that, of course, will be managed by the ACE task framework we've been talking about. This particular service method will block in every thread, waiting for a new message to show up from the half-async part, from the part that's driven by the reactor. And the scheduler of the operating system and the thread scheduling package will decide which of the threads waiting in so-called hungry puppy fashion to get the next GET request, which of those threads will receive the work. The thread will then unblock when GET queue returns, when it's its turn to run, and that GET request will then be extracted out of the message along with the socket handle that comes back, and that will be used to memory map the particular content requested by the user and then send that content back to the client application running on another machine. Notice how, as always, the core web server logic is essentially identical in all the examples we've looked at. The thing that keeps changing is the way in which we arrange this logic to be called using different concurrency and event handling patterns and arrangement of those patterns. Let's take a look now at our thread pool HTTP acceptor class, or TP HTTP acceptor class, which of course is an ACE acceptor, so it registers, uses all the capabilities that ACE acceptor provides. It's parameterized using the TP HTTP handler class, which we looked at earlier, which is a service handler. And its constructor simply forwards down to the constructor of ACE acceptor, which will go and listen on the appropriate port number, in our case, most likely port 80, unless we decide to override that somewhere else. And then if you recall the handle input template method that the acceptor uses when it gets a new connection coming in from a client somewhere in the network, one of the hook methods that the template method handle input calls back is called make service handler. And you can see here we will simply override make service handler in order to be able to spawn a new instance or create a new instance of the TP HTTP handler object. And that will also include a reference to the TP HTTP task object, which is the active object. So what that means is that every endpoint object, which is the one that's the service handler, has a reference to this active object, so it knows how to do a put invocation on that active object to pass the incoming GET messages from the async layer up to the sync layer, where things can be running and blocking in different threads of control. Let's take a look at the driver program for our solution. As you can see here, the driver program is very, very similar to the one we saw before, just a little tiny tweak to use a different kind of acceptor, in this case the TP HTTP acceptor that we've just defined. But other than that, we reuse our Reactor HTTP server template that we used before. We go ahead and create ourselves an ACE reactor to drive the event loop. We create an instance of the HTTP server daemon, which will use that reactor to go ahead and do various things to register for deallocations when things get shut down. And then finally, as always with the reactor, we run the event loop. And the event loop will be used to wait for connection requests to come in. And when those connection requests come in, they're accepted. The TP HTTP handlers are created by the acceptor. And then those handlers are used to take the messages, put them in the thread-safe message queue, where they're then processed by threads in the pool of threads running in the TP HTTP task, which is the active object. Seems complicated, but actually it all flows quite nicely from the various parts of the pattern. So to summarize this particular section, this particular part in the module, it turns out that even though there are lots of moving parts, we can keep track of the roles and responsibilities, the way in which those moving parts relate to each other, by a firm understanding of patterns and frameworks. The particular patterns that we are going to use here, or that we've used here, are the half-sync, half-async pattern. And of course, that's going to be able to combine the reactor pattern with the active object pattern. So now we're able to reuse these patterns we've talked about in previous examples. And more importantly, we're also able to reuse not just the design artifacts, but we're also able to reuse the implementations of these design artifacts that are provided by the various frameworks: the ACE reactor framework, the acceptor connector framework, and the ACE task framework. So this gives us both the reuse of the design knowledge that went into understanding how the patterns relate to each other, as well as the implementation knowledge and detailed design knowledge embodied in the source code that we get with the ACE frameworks. Another nice thing about this particular approach is that by trying to more carefully bound the number of threads that we allocate to the number of cores at our disposal in the hardware, we're probably in a better shape to be able to scale up the processing more effectively. We're not allocating hundreds or thousands of threads, most of which are doing nothing most of the time. Instead, we're having about as many threads as there are cores, and then those threads are used to get data out of the endpoints from the sockets, and then queue up that data in the synchronized request queue, where it's eventually processed by the various threads in the active object pool.